Hello there and welcome to Whispered Knowledge. I'm so glad you found your way here tonight. Maybe you've been wondering about the nature of time, or perhaps you're simply the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, this journey through time itself is for you. You've got nothing to do but rest. Let your mind wander, your breathing slow, and your thoughts drift gently as we explore one of the universe's most fundamental yet mysterious dimensions. Take a moment to settle in. Feel the weight of your body against whatever surface supports you. Notice your breath, flowing in and out, marking time in its own ancient rhythm. Your heart beats, another timekeeping mechanism, having kept its steady count since before you were born, marking perhaps 3 billion beats in an average lifetime. You are, in a very real sense, made of clocks. Biological rhythms synchronized to the rotation of the Earth, the orbit around the Sun, the cycles of light and dark that have shaped life for billions of years. Because tonight, we're not just talking about seconds ticking by on a clock. We're diving into the very fabric of reality itself, unraveling what time actually is, how it works, and why it flows in only one direction. From ancient sundials, marking shadows in the dust of long-vanished civilizations, to atomic clocks precise beyond human imagination. From Einstein's revolutionary discoveries that shattered our assumptions about reality, to quantum mysteries that challenge everything we thought we knew. We'll explore 100 fascinating facts about time. This is a journey that spans from the unimaginably brief Planck time, the smallest possible tick of the cosmic clock, to the incomprehensible vastness of cosmic time, the 13.8 billion years since the Big Bang. We'll explore how time bends and stretches, how it connects to space in ways that seem impossible, how it gives the universe its direction, and possibly even its meaning. Some of what you hear may surprise you. Others might spark curiosity as you drift towards sleep. Some facts might challenge your assumptions. Others might simply be beautiful to contemplate as you relax. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time, discovering that the universe is far stranger and more wonderful than we ever imagined. Now, let's begin our journey through time, the dimension we inhabit but never fully understand. The nature of time. Time is change. In physics, the definition of time is beautifully simple, almost poetic in its directness. Time is change, or more precisely the interval over which change occurs. It's impossible to know that time has passed unless something changes. Think about it for a moment. Really contemplate this strange truth. Without the movement of clock hands, without the sun crossing the sky, without your heartbeat or breath, without any change at all, time itself would be imperceptible, unknowable, perhaps even meaningless. Imagine a universe completely frozen, every particle perfectly still, no vibrations, no motions, no transformations of any kind. In such a universe, would time exist? How could you tell that a second had passed versus a year or a million years? The very measurement of time requires observing some physical quantity that transforms from one state to another. A pendulum swinging, an atom vibrating, a star burning. These are all clocks because they change in predictable ways. Even the decay of a radioactive atom, the rotation of the Earth, the oscillation of light waves, all are manifestations of change that allow us to mark time's passage. This fundamental connection between time and change underlies everything we'll explore tonight. It suggests that time and the physical universe are inseparable, that time doesn't exist as some abstract container waiting to be filled with events, but rather emerges from the events themselves, from the ceaseless transformation of the cosmos, from one state to another. Time may not be a fundamental dimension of reality. This is where things get truly strange. While we experience time as an absolute, flowing river carrying us from past to future, some physicists working on unifying quantum mechanics with gravity have proposed that time might emerge from deeper, more fundamental processes, rather than being built into the fabric of reality itself. This remains highly speculative and debated, but the possibility suggests that time, in this view, might be something like temperature, a useful concept that describes the behavior of many particles, but doesn't exist at the most basic level. If such theories prove correct, the universe at its deepest quantum foundations may be timeless, with time emerging only when we zoom out to the macroscopic world we inhabit. Classical physics treated time as absolute. For centuries, the view of time promoted by Isaac Newton dominated scientific thinking. In this framework, time is absolute, independent of any perceiver, progressing at a consistent pace for everyone everywhere throughout the universe. Newtonian time is essentially imperceptible and mathematical in nature. It flows uniformly, like an invisible river that carries all events forward at the same rate, whether you're standing still or moving, whether you're on Earth or traveling through space. This accords with most people's everyday experience of how time flows. A second is a second, an hour is an hour, regardless of who you are or where you're located. Einstein shattered the notion of absolute time. Everything changed in 1905 when Albert Einstein, a young patent clerk in Bern, Switzerland, published his theory of special relativity. Working in relative isolation, thinking deeply about the nature of light and motion, Einstein came to conclusions so radical they would overturn centuries of scientific consensus. He demonstrated that time is not absolute, but relative, fundamentally intertwined with space to form a four-dimensional continuum called space-time. In Einstein's universe, time is malleable, elastic, stretching and compressing depending on how fast you're moving and how deep you are in a gravitational field. Time, it turns out, passes differently for different observers. This wasn't philosophical speculation, but mathematical fact, backed by equations that made precise, testable predictions. Someone moving at high speed experiences time more slowly than someone standing still. Someone deep in a gravitational well experiences time more slowly than someone far from massive objects. Time became observer-dependent, a revolutionary concept that overturned millennia of assumptions. No longer was there a universal clock ticking the same for everyone everywhere. Instead, each observer carries their own time, their own measure of duration, and these times need not agree. The universe, Einstein revealed, is far stranger than our everyday experience suggests. What feels like absolute, universal time flowing uniformly is actually just the limited perspective of beings moving slowly through weak gravitational fields. Step outside those limitations, and time itself transforms. Time is a dimension like space. In the framework of special relativity, time is not separate from the three spatial dimensions we're familiar with: up, down, left, right, forward, backward. Instead, it forms a fourth dimension, interwoven with length, width, and height to create space-time, a single unified four-dimensional continuum. Events in the universe are not just located in space, at some set of coordinates, x, y, z, but in space-time, defined by four coordinates, three spatial and one temporal. This means that all times, past, present, and future, exist in space-time just as all points in space exist. From this view, sometimes called the block universe perspective or eternalism, the past hasn't disappeared into nothingness, and the future doesn't not yet exist. Rather, while all moments are equally real, laid out along the dimension of time, much like cities are laid out along a highway. Your birth, your first day of school, this moment right now, your eventual death, all exist as four-dimensional events in the block of space-time. We simply experience them sequentially due to the nature of consciousness, like a reader moving through a book page by page, even though all the pages exist simultaneously. This view suggests that the flowing, changing nature of time we experience is an illusion of consciousness, a feature of how we perceive reality rather than a fundamental feature of reality itself. The universe, in this view, simply exists as a four-dimensional block, unchanging and eternal, with the passage of time being how conscious minds navigate through it. The speed of light is constant for all observers. One of Einstein's most profound insights was that the speed of light in vacuum is constant, approximately 299,792,458 meters per second, and this speed is the same for all observers regardless of how fast they're moving. This seemingly simple statement has extraordinary implications. If you're on a train moving at half the speed of light and you shine a flashlight forward, someone standing on the platform doesn't see the light moving at 1.5 times the speed of light. They see it moving at exactly the speed of light. For this to work, time itself must adjust. Time must slow down for the person on the train. This is time dilation, and it's not theoretical speculation. It's been proven in countless experiments. Time dilation is real and measurable. Moving clocks tick more slowly than stationary ones. This isn't an illusion or a malfunction. It's a fundamental property of how time works in our universe. The faster you move through space, the slower you move through time. At everyday speeds, this effect is imperceptibly tiny. But as you approach the speed of light, it becomes dramatic. A clock on a spacecraft traveling at 90% the speed of light would tick at less than half the rate of a clock on Earth. For the traveler, time would feel normal, seconds passing as they always do. But when they returned home, they'd find that much more time had passed on Earth. They would have aged less than those who stayed behind. The famous twin paradox made real. Gravity also dilates time. Einstein's general theory of relativity, published in 1915, revealed another form of time dilation. Massive objects curve space-time around them, and this curvature affects how time flows. The stronger the gravitational field, the slower time passes. Someone standing at sea level on Earth experiences time flowing slightly more slowly than someone at the top of a mountain. The difference is tiny, measured in nanoseconds, but it's real and measurable. Near extremely massive objects like neutron stars or black holes, time dilation becomes extreme. At the event horizon of a black hole, from the perspective of a distant observer, time appears to stop altogether. Someone falling into a black hole would experience time normally, but to someone watching from far away, the falling person would appear to slow down, freeze, and never quite cross the horizon, frozen in time forever. Time may be quantized at the smallest scales. At the everyday level, and even at atomic scales, time appears continuous, flowing smoothly from one moment to the next with infinite divisibility. But at the Planck scale, the smallest meaningful scale in physics, time itself may come in discrete units. The Planck time, approximately 5 times 10 to the negative 44 seconds, represents the smallest possible tick of time that makes physical sense. Below this threshold, our current theories of physics break down. Quantum fluctuations of space-time itself become significant, and the very concepts of time and space lose their usual meanings. Whether time is truly quantized, made up of individual moments like frames in a film, or whether the Planck time merely represents a measurement limit remains an open question at the frontiers of physics. Time has different definitions across physics. Depending on which branch of physics you're working in, time takes on different characteristics. In thermodynamics, time is a direction, pointing from past to future in the direction of increasing entropy. In quantum mechanics, time is typically treated as an independent parameter that marks the evolution of quantum states, external to the system being described. In general relativity, time is part of the dynamic space-time continuum, curved by mass and energy. In cosmology, cosmic time provides a universal reference frame tied to the expansion of the universe. Each of these frameworks offers a different perspective on what time is and how it behaves, and reconciling these different views remains one of the great challenges in theoretical physics. The present moment has no duration. If you try to pin down the present, to isolate this moment of now, you find it has no thickness, no duration. The present is the infinitesimally thin boundary between past and future, a dimensionless point sliding along the timeline. Any duration, no matter how brief, already contains past moments and future moments. The now we experience is not a single instant, but a window of perception, what psychologists call the specious present, typically lasting a few hundred milliseconds to a few seconds. Our brains integrate sensory information over this window and present it to consciousness as the experience of now. But physically, the true present has no extension in time. It's a mathematical abstraction, the limit as duration approaches zero. We only experience time in one direction. Unlike the three spatial dimensions, where we can move freely back and forth, we experience time as having a direction. We remember the past, experience the present, and anticipate the future, never the reverse. This asymmetry, called the arrow of time, is one of the deepest mysteries in physics. The fundamental laws that govern particles and forces are largely time-symmetric. If you ran them backward, they would still work. Yet, we never see shattered glasses spontaneously reassembling. We never see heat flowing from cold to hot. We never see smoke gathering into unburned wood. The universe has a direction, an arrow pointing from organized past toward disordered future. Where this arrow comes from and why time flows in only one direction remains a question that touches on thermodynamics, cosmology, consciousness, and the deepest nature of reality itself. Ancient timekeeping and human history. Humans have measured time for thousands of years. Long before mechanical clocks or even written language, our ancestors tracked time by observing the sky. The predictable patterns of celestial bodies provided the first calendars and clocks. The rising and setting of the sun marked days. The phases of the moon marked months. The changing positions of stars marked seasons and years. These were not just scientific observations, but vital knowledge for survival. Knowing when to plant crops, when to expect floods, when to prepare for winter, all depended on understanding time's passage through careful observation of the heavens. The oldest known calendar may be 30,000 years old. Archaeologists have discovered ancient bones with deliberate markings that appear to track lunar cycles. The Ishango bone from Central Africa, dating back some 20,000 years, contains systematic notches that some researchers interpret as a lunar calendar. Similar artifacts from Europe and Asia suggest that even our distant Paleolithic ancestors were keeping track of time, counting days and months, perhaps for ritual purposes or to predict seasonal changes. These ancient tally marks represent humanity's first attempts to not just experience time, but to record it, measure it, and thereby gain some control over it. Ancient Egyptians divided the day into sections. By around 3,500 years ago, the Egyptians had developed sophisticated timekeeping systems. They divided daylight into 12 parts, the origin of our 12-hour system. They used shadow clocks and obelisks, essentially elaborate sundials, to track the sun's movement across the sky. These devices didn't just tell time, they were integrated into Egyptian culture, influencing religious ceremonies, agricultural schedules, and the organization of labor. The positioning of shadows marked not just hours, but moments of ritual significance in a civilization deeply intertwined with the rhythms of time. Water clocks measured time when the sun didn't shine. Sundials had an obvious limitation. They only worked when the sun was visible. To measure time at night or on cloudy days, ancient civilizations developed water clocks, or clepsydras, elegant devices that harness the steady flow of water to mark the passage of hours. These devices allowed water to drip from one container to another at a controlled rate. By marking the containers with lines or graduations, observers could track the passage of time independent of celestial observations. The oldest surviving water clocks date to around 1500 years before the Common Era, found in the tombs of Egyptian pharaohs and in Babylon's temples. But these weren't simple vessels. They represented sophisticated engineering. Some incorporated gears and automation. Others featured moving figures that appeared at certain hours, primitive automata driven by the patient drip of water. The Tower of the Winds in Athens, built in the 1st century before the Common Era, housed an elaborate water clock alongside its sundials, combining multiple timekeeping methods in a single monument. For nearly 2,000 years, until the invention of mechanical clocks in medieval Europe, water clocks represented the state of the art in timekeeping precision. Chinese engineers created particularly elaborate versions, with Susong's astronomical clock tower in the 11th century standing over 30 feet tall and featuring a complex system of scoops, wheels, and water-driven mechanisms that could track both time and astronomical positions. These devices weren't just functional tools, but works of art, testaments to humanity's determination to measure and mark the flowing stream of time. The Babylonians gave us 60-second minutes. The sexagesimal system, using 60 as a base, originated with the ancient Sumerians and Babylonians. Why 60? The Babylonians likely chose it because 60 is highly divisible. You can divide it evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, making calculations easier. This system survived through millennia and across civilizations. Today, we still divide hours into 60 minutes and minutes into 60 seconds, a direct inheritance from Mesopotamian mathematics developed over 4,000 years ago. Every time you glance at a clock, you're using a timekeeping system with roots in the ancient Near East. Mechanical clocks appeared in the 13th century. The invention of the mechanical clock in medieval Europe marked a revolution in timekeeping. These early clocks used a verge escapement mechanism, allowing a falling weight to drive gears at a controlled rate. The first mechanical clocks didn't have minute hands, or even hour hands in some cases. They were primarily used in monasteries to ring bells at regular intervals for prayer, but their impact was profound. For the first time, time could be tracked continuously, independent of the sun or weather. This technology gradually spread from churches to town squares, and the public display of mechanical time began to reorganize society around abstract temporal units rather than natural rhythms. Pendulum clocks brought unprecedented accuracy. In 1656, Dutch scientist Christian Huygens invented the pendulum clock. A pendulum swings at a remarkably consistent rate, determined by its length and local gravity. Huygens realized this could regulate a clock mechanism far more accurately than previous designs. His pendulum clocks could keep time to within seconds per day, a dramatic improvement. Over the following centuries, refinements brought pendulum clocks to accuracies of a fraction of a second per day. For nearly 300 years, the pendulum clock reigned as the most accurate timekeeper available, essential for navigation, science, and the coordination of an increasingly interconnected world. The search for precise time drove maritime navigation. Determining longitude at sea required knowing the exact time. If a ship's captain knew the time at a reference location and could compare it to local solar time, the difference would reveal how far east or west they'd traveled. But keeping accurate time on a rolling ship proved extremely difficult. Pendulum clocks didn't work well at sea, and temperature changes affected clock mechanisms. In 1714, the British government offered a massive prize for a solution to the longitude problem. Clockmaker John Harrison devoted his life to creating marine chronometers, clocks that could maintain accuracy despite ship motion and temperature variations. His designs eventually succeeded, revolutionizing navigation and making the oceans safer for travel and trade. Precise timekeeping quite literally expanded the reach of human civilization. Standardized time zones were created for railroads. For most of human history, local time was determined by the sun. Noon occurred when the sun reached its highest point in the sky, which happens at slightly different moments in different locations. This created chaos when railroads began connecting distant cities. A train schedule listing a departure time of 3 o'clock meant different things in different towns. In the 1880s, the world divided into standardized time zones, each typically 15 degrees of longitude wide, corresponding to 1 hour of time difference. Railroad companies drove this standardization, but it soon became universal. Suddenly, time became synchronized across vast distances, enabling the coordination that modern global civilization requires. Atomic clocks are accurate to billionths of a second. The quest for ever more precise timekeeping reached entirely new heights with the development of atomic clocks in the mid-20th century. These remarkable devices measure time based on the extremely consistent oscillations of atoms, particularly cesium atoms, though rubidium, hydrogen, and other elements have also been used. The principle is elegant. Atoms can only exist in specific energy states, and when they transition between these states, they absorb or emit electromagnetic radiation at very precise frequencies. For cesium, the frequency used for timekeeping is in the microwave range, about 9.2 gigahertz. This frequency is extraordinarily stable, unaffected by temperature, pressure, magnetic fields, or virtually any environmental factor that would influence mechanical or electronic clocks. It's determined by the fundamental physics of the cesium atom itself, by the quantum mechanical properties that govern how its electrons arrange themselves. This makes atomic clocks not just precise, but reproducible anywhere in the universe where cesium exists. The second is now officially defined as the duration of 9,192,631,770 periods of radiation corresponding to a specific transition in cesium-133 atoms. This definition, adopted in 1967, replaced previous definitions based on Earth's rotational orbit, which are irregular and gradually changing. Modern cesium atomic clocks are so precise they would gain or lose less than 1 second over tens of millions of years. The most advanced versions achieve uncertainties of about 1 part in 10 to the 16th, meaning they would take tens of millions of years to drift by even a single second. This extraordinary accuracy isn't just scientific curiosity or academic achievement. It's essential for GPS navigation, which requires nanosecond precision to determine positions accurately. It's crucial for telecommunications, where different systems must be precisely synchronized. It's necessary for high-frequency trading in financial markets, where microseconds can mean millions of dollars. It's fundamental to radio and television broadcasting, to power grid synchronization, to deep space navigation, to scientific experiments pushing the boundaries of physics. The modern world's infrastructure increasingly depends on precise, universally agreed upon time, making atomic clocks and time distribution systems critical infrastructure, as important as roads or power lines. The most accurate clock loses 1 second every 30 billion years. Researchers continue pushing the boundaries of precision. Optical lattice clocks, which trap atoms in a grid of laser light and measure even higher frequency oscillations than cesium clocks, have achieved mind-boggling accuracy. The most advanced optical atomic clocks are now accurate to within 1 part in 10 to the 18th power, meaning they would lose only about 1 second over the current age of the universe, roughly 13.8 billion years, and would need to run for more than twice that long before drifting by a second. At these precision levels, the clocks are sensitive enough to measure the time dilation effects of being raised just a few centimeters higher in Earth's gravitational field. Precise timekeeping revealed relativity in action. One of the most beautiful confirmations of Einstein's theories came from atomic clocks. In 1971, physicists Joseph Haffel and Richard Keating conducted an experiment where they flew atomic clocks around the world on commercial airliners, some traveling eastward, others westward. When they compared these traveled clocks to clocks that remained on the ground, they found tiny differences in elapsed time, measured in nanoseconds, exactly as predicted by special and general relativity. The clocks experience time dilation due to their motion and due to being at altitude where gravity is slightly weaker. This experiment, and many others like it, have proven beyond any doubt that time really does flow at different rates in different circumstances. Time perception varies between species. Not all creatures experience time the same way. Animals with faster metabolisms and smaller body sizes tend to perceive time more slowly than larger animals. A fly, for instance, experiences roughly 4 times as many moments per second as a human, which is why they're so difficult to swat. From their perspective, your hand is moving in slow motion. Different animals also have different flicker fusion rates, the speed at which separate images blur into continuous motion. Humans see smooth motion in videos at around 24 frames per second, but a dog needs closer to 70 frames per second, and some birds require even higher rates. Time, as a subjective experience, scales with biology in fascinating ways. Relativity and Einstein's revolution. Special relativity changed everything in 1905. When Albert Einstein was working as a patent clerk in Bern, Switzerland, he published a paper that would revolutionize physics. His special theory of relativity introduced the world to concepts that seem to defy common sense, but have proven to be fundamental truths about our universe. The theory started with 2 simple postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light in vacuum is constant for all observers regardless of their motion. From these 2 assumptions, Einstein derived consequences that shattered the Newtonian worldview that had dominated for centuries. Simultaneity is relative. One of the most counterintuitive results of special relativity is that whether 2 events occur at the same time depends on the observer's motion. Two events that are simultaneous for one observer may not be simultaneous for another observer, moving relative to the first. Imagine a train moving past a platform. Lightning strikes the front and back of the train. Someone standing on the platform, equidistant from both strikes, sees them happen simultaneously. But someone on the train, moving toward the front strike and away from the rear strike, will see the front strike first. Both observers are correct from their frame of reference. There is no absolute universal now that applies throughout the universe. Simultaneity is a relative concept, dependent on one's state of motion. Nothing can travel faster than light. In Einstein's universe, the speed of light is not just a speed limit, it's a fundamental feature of space-time itself. As objects accelerate toward the speed of light, they gain mass, and it requires ever more energy to accelerate them further. To actually reach the speed of light would require infinite energy. Only massless particles like photons can travel at light speed. This cosmic speed limit has profound implications. It means that faster than light travel is not just technologically difficult, but appears to be fundamentally impossible. It also means that the universe has a built-in communication delay. Light from the sun takes about 8 minutes to reach Earth. So we see the sun as it was 8 minutes ago, not as it is right now. Mass and energy are equivalent. Einstein's most famous equation, E equals mc squared, expresses the equivalence of mass and energy. A small amount of mass contains an enormous amount of energy. Energy equals mass times the speed of light squared. This relationship explains how stars shine, converting mass into energy through nuclear fusion. It explains nuclear weapons and nuclear power. It also means that energy has mass. A hot object is very slightly heavier than the same object when cold. A compressed spring is slightly heavier than a relaxed spring. Even light, though massless, carries energy and therefore contributes to gravitational fields. Mass and energy are two forms of the same underlying quantity, interconvertible under the right conditions. Moving objects contract in length. According to special relativity, objects moving at high speeds appear contracted along their direction of motion, as measured by a stationary observer. A spacecraft traveling at 90% the speed of light would appear to be about 44% of its rest length. This isn't an optical illusion or a measurement error. It's a real physical effect called length contraction. However, to the people on the spacecraft, everything appears normal. They measure themselves as having normal length. It's the external universe that appears contracted in their direction of motion. Space and time trade off in a way that preserves the speed of light as constant for all observers. Moving clocks run slow. Time dilation, the slowing of time for moving objects, is perhaps the most famous consequence of special relativity. If you could watch a clock on a spacecraft moving at very high speed relative to you, you would see it ticking more slowly than your own clock. The effect is symmetric. Astronauts on the spacecraft looking back at you would see your clock running slow. This seems paradoxical until you realize that the situation isn't symmetric if the spacecraft turns around and comes back. The traveling clock will have recorded less elapsed time, the twin paradox. The traveler ages less than the stay-at-home twin. This has been confirmed countless times with atomic clocks on aircraft and satellites. Space-time is four-dimensional. In special relativity, space and time merge into a single four-dimensional continuum. An event is specified by 4 coordinates, 3 spatial coordinates telling where it happened, and 1 temporal coordinate telling when. Different observers may disagree about the spatial and temporal separations between events, but they agree on the space-time interval, a combination of space and time differences that remains the same for all observers. This unified view of space-time reveals deep connections between space and time, connections that become even more profound in general relativity when gravity enters the picture. General relativity describes gravity as curved space-time. In 1915, Einstein published his general theory of relativity, extending his ideas to include gravity. In this framework, gravity is not a force in the traditional sense. Instead, mass and energy curve the fabric of space-time itself, and objects moving through this curved space-time follow geodesics, the shortest paths through the curved geometry. Planets orbit the sun, not because they're pulled by an invisible force, but because the sun's mass has curved space-time around it, and the planets are following the natural paths through this curved geometry. As physicist John Wheeler famously summarized, space-time tells matter how to move. Matter tells space-time how to curve. Black holes represent extreme space-time curvature. When a massive star collapses, it can create a region of space-time so intensely curved that nothing, not even light, can escape. This is a black hole. At the center lies a singularity where curvature becomes infinite and our theories break down. Surrounding the singularity is the event horizon, the point of no return. Time dilation near a black hole becomes extreme. To an outside observer, someone falling toward a black hole appears to slow down, their clock ticking slower and slower, until, at the event horizon, they seem to freeze, asymptotically approaching but never quite crossing the boundary. To the falling person, time continues normally, and they would cross the horizon in finite time by their own clock, though they could never send information back across it. Gravitational waves are ripples in space-time. Einstein's general relativity predicts that accelerating masses create ripples in the fabric of space-time itself, gravitational waves traveling at the speed of light. For decades, these remained theoretical. Then, in 2015, the LIGO detectors made the first direct detection of gravitational waves from two merging black holes over 1 billion light years away. The signal showed space-time itself oscillating, stretching and squeezing by an amount smaller than the width of an atomic nucleus. Since then, gravitational wave astronomy has opened a new window on the universe, detecting dozens of events involving black holes and neutron stars, providing unprecedented tests of general relativity in the most extreme environments. GPS would fail without relativistic corrections. One of the most practical and everyday applications of relativity is the global positioning system. Your smartphone, your car's navigation system, aircraft, ships, surveyors, emergency services, all rely on GPS, and GPS would be completely useless without accounting for Einstein's theories of relativity. This isn't theoretical physics in an ivory tower. It's applied relativity working billions of times every day. GPS satellites orbit at about 20,000 kilometers altitude, roughly 12,500 miles above Earth's surface, traveling at roughly 14,000 kilometers per hour, about 8,700 miles per hour. At this altitude, gravity is weaker than at Earth's surface, about 4 times weaker in fact. General relativity predicts that clocks in weaker gravitational fields tick faster. Specifically, the satellite clocks will tick faster by about 45 microseconds per day, compared to identical clocks on Earth's surface. That's 45 millionths of a second, a tiny amount, but crucial. But the satellites are also moving, and they're moving fast. Special relativity predicts that moving clocks tick slower than stationary ones. The satellite clocks are moving at about 14,000 kilometers per hour, relative to someone standing on Earth's surface. This velocity causes the clocks to tick slower by about 7 microseconds per day. So we have two competing effects. Gravity makes the clocks run fast by 45 microseconds. Velocity makes them run slow by 7 microseconds. The combined effect is that satellite clocks gain about 38 microseconds per day, the difference between the two effects. 38 microseconds might not sound like much, but light travels at nearly 300,000 kilometers per second. In 38 microseconds, light travels about 11 kilometers, roughly 7 miles. Without correcting for these relativistic effects, GPS positions would accumulate errors of about 10 to 15 kilometers per day. Within hours, the system would be giving you positions kilometers away from your actual location, rendering it utterly useless for navigation. After a month, the accumulated error would be over 300 kilometers. The system would be worthless. To prevent this, engineers set the satellite clocks to run at a slightly different frequency before launch. The satellite's atomic clocks are set to tick at 10.2, 299,999,543 megahertz instead of the standard 10.23 megahertz. This slight adjustment compensates for the time dilation effects. Once in orbit, experiencing both gravitational and velocity-induced time dilation, these clocks tick at exactly the right rate to stay synchronized with ground clocks. Every time your phone tells you your location within a few meters, it's using Einstein's theories of relativity. Without relativity, GPS simply wouldn't work. Time stops at the event horizon of a black hole. From the perspective of a distant observer, time slows down dramatically near a black hole's event horizon. An observer watching something fall toward a black hole would see it slow down, redden, and fade, appearing to take infinite time to reach the horizon. This is an extreme case of gravitational time dilation. However, for the falling object itself, time passes normally. They would cross the event horizon in finite time by their own clock, experiencing nothing special at the moment of crossing, though tidal forces might be tearing them apart. The event horizon represents a boundary where time, from an outside perspective, grinds to a halt. Time in quantum mechanics. Quantum mechanics treats time differently. In quantum theory, time plays a fundamentally different role than in relativity. While position, momentum, and energy are represented by quantum operators that can exist in superposition states, time is typically treated as a classical parameter, an external label marking the evolution of quantum systems. This asymmetry between time and other quantities has puzzled physicists for decades. Some interpretations of quantum mechanics suggest that time itself might emerge from quantum processes at a deeper level, but there's no consensus on this question. The uncertainty principle connects time and energy. Werner Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics, states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. There's a similar relationship between time and energy. The more precisely you know when a quantum event occurs, the less precisely you can know the energy involved, and vice versa. This isn't a limitation of measurement tools, but a fundamental feature of reality. A particle that exists for only a very brief time interval can have a very uncertain energy. This allows for the temporary violation of energy conservation through the creation of virtual particles, which pop into existence and annihilate on timescales so brief that their energy uncertainty covers their rest mass. Time is not an operator in quantum mechanics. Unlike position or momentum, time in standard quantum mechanics is not represented by an operator. This has led to various philosophical and technical difficulties, particularly when trying to ask questions like, what is the probability that a particle will be found at a particular position at a particular time. Various proposals for a time operator have been made, but none have gained universal acceptance. This asymmetry between time and space in quantum mechanics stands in stark contrast to their unified treatment in relativity, pointing to deep unresolved tensions between our two most successful physical theories. Quantum entanglement appears to act instantaneously. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. This seems to violate relativity's prohibition against faster-than-light communication. However, the resolution is subtle. While the correlation is instantaneous, no information can be transmitted this way. The results of measurements on entangled particles are random, and only when you compare results from both locations, which requires classical communication at light speed or slower, do you see the correlation. Entanglement doesn't allow faster-than-light signaling, though it does reveal non-local connections that Einstein called spooky action at a distance. Time reversal symmetry is almost perfect. Most fundamental laws of physics work equally well, whether time runs forward or backward. If you filmed particles interacting and played the video in reverse, the reverse process would also obey physical laws. This is called time reversal symmetry. However, certain rare processes involving the weak nuclear force do violate time reversal symmetry, albeit very slightly. These violations are connected to the predominance of matter over antimatter in our universe. But for the vast majority of quantum processes, there's no intrinsic direction of time at the microscopic level, making the arrow of time we experience in everyday life even more mysterious. Radioactive decay is fundamentally unpredictable. Quantum mechanics introduces true randomness into the universe. When a radioactive atom will decay cannot be predicted, even in principle. You can calculate the probability that it will decay within a given time period, but the exact moment of decay is fundamentally indeterminate. This isn't due to hidden variables or lack of information. It's a basic feature of quantum reality. Time, in the quantum realm, does not determine the future completely. The universe contains genuine probabilistic elements that make the future open rather than predetermined. The Schrödinger equation governs time evolution. In quantum mechanics, the time evolution of a quantum system is described by the Schrödinger equation. This equation tells you how the wave function, which encodes all possible information about a quantum system, changes over time. The wave function evolves smoothly and deterministically between measurements, but when a measurement occurs, the wave function collapses into one of many possible states, a process that seems to introduce a fundamental role for observation and consciousness in physics, leading to ongoing debates about the interpretation of quantum mechanics. Quantum tunneling allows particles to borrow time. In quantum mechanics, a particle can sometimes pass through a barrier that classical physics says it shouldn't be able to cross. This is quantum tunneling, essential to many processes, including radioactive decay and the nuclear fusion that powers the sun. The particle appears to violate energy conservation temporarily, borrowing energy to cross the barrier and paying it back on the other side. Heisenberg's energy-time uncertainty principle allows this temporary borrowing as long as it happens quickly enough. Time, at the quantum level, permits transient violations of classical conservation laws. The quantum Zeno effect can freeze time. If you continuously observe a quantum system to see if it has changed state, the act of observation can prevent the change from occurring. This is the quantum Zeno effect, named after Zeno's paradox. Frequent measurements can effectively freeze the evolution of a quantum system. Conversely, the quantum anti-Zeno effect shows that measurements at certain intervals can accelerate decay, These effects demonstrate the deep connection between measurement and time evolution in quantum mechanics, suggesting that observation itself plays a role in how quantum time unfolds. Time crystals are a new phase of matter. In 2012, physicist Frank Wilczek proposed the existence of time crystals, systems that exhibit periodic structure in time, the way ordinary crystals have periodic structure in space. For years, these seemed impossible, violating fundamental principles. But in 2016, researchers created time crystals in the laboratory, systems that oscillate perpetually without consuming energy, seemingly violating energy conservation. However, they don't actually create perpetual motion or violate thermodynamics. Time crystals represent a new phase of matter that exists in a non-equilibrium state, periodically returning to the same configuration at regular time intervals, crystals that tick like clocks at the quantum level. The arrow of time and entropy. The arrow of time points toward increasing disorder. The second law of thermodynamics states that in an isolated system, entropy, a measure of disorder or randomness, tends to increase over time. This fundamental principle gives time a direction, an arrow pointing from organized past toward chaotic future. You can tell which direction is forward in time by observing whether entropy is increasing. Watch ice melt in warm water, never reforming. Observe coffee cooling to room temperature, never spontaneously warming. See a glass shatter into countless fragments, never reassembling itself. These everyday irreversibilities, happening all around us constantly in countless forms, all point in the same direction, from past to future, from order to disorder, from low entropy to high entropy. This is the thermodynamic arrow of time, and it's why we remember yesterday, but not tomorrow. Why we can predict the future statistically, but not with certainty. Why causes precede effects, and not the reverse. The arrow is subtle and pervasive. A deck of cards shuffled becomes disordered, never spontaneously ordering itself into neat sequences. Perfume disperses through a room, never gathering back into its bottle. Heat flows from hot to cold. Energy dissipates. Structures decay. The universe, it seems, has a direction, a one-way flow from the special, ordered, low entropy state in which it began toward an ultimate fate of maximum entropy and equilibrium. Entropy is a measure of disorder or randomness. Entropy quantifies the number of microscopic arrangements that correspond to the same macroscopic state. A highly ordered system, like ice crystals, can only be arranged in relatively few ways at the molecular level. A disordered system, like water vapor, can be arranged in vastly more ways. The more ways a system can be internally arranged while looking the same macroscopically, the higher its entropy. The second law says that isolated systems evolve towards states with higher entropy simply because there are more ways to be disordered than ordered, and random processes tend to explore all available states. The universe began in extremely low entropy. The early universe, just after the Big Bang, was incredibly hot and dense, which might sound disordered, but actually, it was in a state of very low entropy. Matter and energy were distributed smoothly and uniformly. As the universe evolved, gravity caused this smooth distribution to clump into stars, galaxies, and complex structures. While this might seem like increasing order, the overall entropy of the universe increased dramatically. Stars burn, converting ordered hydrogen into disordered radiation and heat. Black holes form, representing states of maximum entropy. The low entropy initial state of the universe is what allows the arrow of time to exist. Without it, there would be no preferred direction of time. We remember the past, but not the future. Our experience of time has a direction. You remember what you had for breakfast this morning, but you don't remember what you'll have tomorrow. This psychological arrow of time aligns with the thermodynamic arrow. Memory formation is a physical process that increases entropy. When your brain encodes a memory, it creates ordered correlations between neurons and external events. But this process generates heat and increases overall entropy. The ability to form memories, and therefore to distinguish past from future, depends on the universe having a direction of increasing entropy. Cause precedes effect due to entropy. We experience causation as flowing from past to future. Striking a match causes a flame. The flame doesn't cause the striking. This causal arrow is deeply connected to entropy. Controlling the future, making something happen, requires setting up low entropy initial conditions and allowing them to evolve toward higher entropy final states. The relationship between cause and effect emerges from the thermodynamic arrow of time. In a universe without increasing entropy, there would be no meaningful distinction between cause and effect, and the very structure of how we understand events unfolding would collapse. Most physical laws are time reversible. Here's the paradox. The fundamental laws governing particles and forces are almost entirely symmetric in time. Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations, all work equally well whether time runs forward or backward. If you filmed particles interacting and ran the film in reverse, the reversed interactions would still obey the fundamental laws. Yet we never see macroscopic time reversal. We never see smoke gathering back into unburned wood or shattered glass spontaneously reassembling. The microscopic laws are time symmetric, but the macroscopic world is not. This is one of the deepest mysteries in physics. The second law is statistical, not absolute. The second law of thermodynamics is not like other physical laws. It's statistical. It doesn't say entropy must always increase. It says entropy is overwhelmingly likely to increase. In principle, all the air molecules in a room could spontaneously gather in one corner, leaving a vacuum elsewhere. This doesn't violate any fundamental law of physics, but the probability is so astronomically small that it would never happen over the lifetime of the universe. With a macroscopic number of particles, typically on the order of 10 to the 23rd particles, the statistical likelihood becomes a practical certainty. Entropy increase is not impossible to violate, merely overwhelmingly improbable. Loschmidt's paradox questions time's arrow. If the microscopic laws are time reversible, how can macroscopic behavior be irreversible? This is Loschmidt's paradox. If you have a gas expanding to fill a box, you could, in principle, reverse every particle's velocity at some instant. The reverse system would obey all the same laws, and the gas would spontaneously contract back to one corner. So why don't we see this happen? The answer lies in initial conditions. The contracted gas represents a very special, low entropy state. If you randomly selected initial conditions from all possible states, you would almost never choose such a special one. The arrow of time doesn't come from the laws themselves, but from the special, low entropy initial conditions of our universe. Maxwell's demon challenged the second law. In 1867, James Clerk Maxwell imagined a tiny demon who could sort molecules, allowing fast ones through a door in one direction and slow ones in the other, effectively decreasing entropy without doing work, violating the second law. For decades, this thought experiment puzzled physicists. The resolution came from realizing that the demon must process information about which molecules are approaching, and erasing this information requires energy and increases entropy. Information itself, has thermodynamic properties. The demon can't violate the second law because the act of measurement and information processing generates entropy. This insight connected thermodynamics, information theory, and computation in deep ways. The heat death of the universe is entropy maximization. If entropy continually increases, where does it end? The ultimate fate predicted by thermodynamics is the heat death of the universe, a state of maximum entropy where all energy is evenly distributed, all temperature differences have been eliminated, and no work can be extracted. Stars will burn out, black holes will evaporate through Hawking radiation, and eventually, everything will reach thermal equilibrium at a uniform, near absolute zero temperature. Time, in a sense, would end, not because time itself stops, but because nothing would change anymore. Without change, without energy differences to drive processes, time would become meaningless. This fate, if accurate, lies unimaginably far in the future, perhaps 10 to the 100 years or more from now. Different arrows of time may align by coincidence. Several different arrows of time exist. Thermodynamic entropy increasing, electromagnetic radiation spreading outward rather than converging, quantum wave functions collapsing, our psychological experience of past versus future. These all point in the same direction in our universe, from past to future. But are they fundamentally connected, or is their alignment a contingent feature of our particular universe? Some physicists argue they all reduce to the thermodynamic arrow and the low entropy initial conditions of the Big Bang. Others suggest independent arrows that happen to align, unraveling which aspects of time's directionality are fundamental and which are emergent remains an active area of research. Reversing time would reverse entropy increase. If time could somehow run backward, entropy would decrease. Cream would unmix from coffee, heat would flow from cold to hot, and broken objects would reassemble. This seems absurd because we define the forward direction of time as the direction of entropy increase. But some cosmological models suggest that in certain scenarios, perhaps in a contracting phase of the universe following a Big Bang, the thermodynamic arrow might reverse. In such a universe, intelligent beings would still experience time flowing from past to future, but that future would be one of decreasing entropy. They would observe shattered glasses assembling themselves and see that as natural and normal, just as we see them breaking.
Measuring time with precision.
The second is defined by atomic oscillations. Since 1967, the international definition of the second has been based on cesium atoms. Specifically, 1 second is the duration of 9,192,631,770 periods of the radiation, corresponding to the transition between two hyperfine levels of the ground state of cesium-133. This definition provides a standard that is reproducible anywhere in the universe. Any sufficiently advanced civilization with access to cesium could recreate our definition of the second precisely. This represents a shift from definitions based on Earth's rotation or orbit to a truly universal standard. Atomic clocks revolutionized precision. Before atomic clocks, the most accurate timekeepers were pendulum clocks and quartz crystal oscillators. Atomic clocks, first developed in the 1950s, offered a quantum leap in precision. They work by detecting the resonant frequency of atoms, typically cesium or rubidium, as they transition between energy levels. These transitions occur at extraordinarily consistent frequencies, unaffected by temperature, pressure, or other environmental factors that influence mechanical or electronic clocks. Modern cesium atomic clocks are accurate to about 1 part in 10 to the 15th, meaning they would neither gain nor lose a second over tens of millions of years. Optical clocks surpass cesium standards. The latest generation of atomic clocks uses optical transitions in atoms, like strontium or ytterbium, because light oscillates at much higher frequencies than microwave radiation used in cesium clocks. Optical clocks can measure time even more precisely. The best optical lattice clocks achieve uncertainties below 1 part in 10 to the 18th. They're so sensitive they can detect the gravitational time dilation caused by raising the clock by just 2 centimeters. These clocks are not only research tools, but are being considered as the next generation of time standards, potentially redefining the second in terms of optical rather than microwave transitions. UTC coordinates world time, Coordinated Universal Time, abbreviated UTC, serves as the world's time standard. It's based on International Atomic Time, which averages over 400 atomic clocks in laboratories around the globe. However, UTC is occasionally adjusted to keep it aligned with Earth's rotation through the addition of leap seconds. Because Earth's rotation is gradually slowing due to tidal friction with the Moon, atomic time and solar time slowly drift apart. Leap seconds compensate for this drift, ensuring that UTC remains synchronized with astronomical time. Whether to continue using leap seconds or let atomic time drift free from Earth's rotation is currently debated. Leap seconds keep clocks aligned with Earth. A leap second is a 1-second adjustment, occasionally applied to UTC, to account for irregularities in Earth's rotation. Since 1972, 27 leap seconds have been added. These adjustments can cause problems for computer systems and financial networks that assume every minute contains exactly 60 seconds. Some propose abolishing leap seconds and allowing atomic time to drift independently of solar time. Over centuries, this would cause significant divergence. Noon would no longer correspond to the sun's highest point in the sky. The debate highlights a fundamental tension between astronomical time, based on celestial motions, and atomic time, based on fundamental physics. GPS satellites carry atomic clocks. Each GPS satellite contains multiple atomic clocks. The system requires such precision because it determines position by measuring the time it takes signals to travel from satellites to receivers. Light travels about 30 centimeters in 1 nanosecond. To achieve position accuracy of a few meters, GPS must measure time to nanosecond precision. The atomic clocks aboard GPS satellites, combined with ground-based corrections and relativistic adjustments, make this possible. Without atomic clock technology, GPS as we know it simply couldn't exist. Network synchronization requires precise time. The internet and modern telecommunications rely on precise time synchronization. Financial transactions, cellular networks, power grids, and data centers all require accurate timestamps and coordinated timing. Network Time Protocol, or NTP, synchronizes computer clocks across the internet to within milliseconds. More precise applications use GPS-disciplined oscillators or direct connections to atomic clocks. High-frequency trading platforms require microsecond-level synchronization. The modern world's infrastructure increasingly depends on precise, universally agreed-upon time, making atomic clocks and time distribution systems critical infrastructure. Millisecond pulsars are natural clocks. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation. Some millisecond pulsars rotate hundreds of times per second with extraordinary regularity. Their rotation periods are so stable that they can be used as natural clocks, potentially even rivaling atomic clocks in long-term stability. Astronomers use arrays of millisecond pulses as galactic-scale gravitational wave detectors, searching for the subtle changes in pulse arrival times that would indicate gravitational waves passing through the galaxy. These stellar remnants serve as cosmic timepieces billions of years old. Timekeeping enabled the information age. Modern technology fundamentally depends on precise timing. Computer processors use clock speeds to coordinate billions of operations per second. GPS, telecommunications, power distribution, financial markets, scientific experiments all require nanosecond to microsecond precision timing. The progression from sundials marking hours to atomic clocks measuring nanoseconds represents not just improved accuracy, but a qualitative transformation in what humanity can accomplish. Our ability to carve time into increasingly fine divisions and synchronize those divisions globally has enabled the complex, interconnected technological civilization we inhabit. The kilogram is now defined using time. In 2019, the International System of Units was revised. The kilogram, previously defined by a physical artifact, a platinum iridium cylinder kept in France, is now defined in terms of fundamental constants, including the Planck constant. This redefinition relies on extremely precise measurements that in turn depend on atomic clocks. In effect, mass is now defined through its relationship to energy via E equals mc squared, and energy is measured through the frequency of photons, which depends on precise time measurement. Time has become so fundamental to metrology that even mass is ultimately defined through temporal measurements. Time dilation in practice. Astronauts age slightly slower than Earth-bound humans. Astronauts on the International Space Station orbit Earth at about 7.6 kilometers per second. At this speed, special relativity predicts time dilation. The ISS orbits at about 400 kilometers altitude, where gravity is slightly weaker, causing gravitational time dilation in the opposite direction. The combined effect is that astronauts age slightly slower than people on Earth, about 0.007 seconds, less per 6 months in orbit. This has been measured with atomic clocks and confirmed to match predictions precisely. Muons prove time dilation. Cosmic rays striking Earth's upper atmosphere create particles called muons. These particles are unstable, decaying with a half-life of about 2 microseconds. At the speed they travel, muons created at high altitude should decay long before reaching Earth's surface, yet we detect them at ground level in large numbers. Why? From our reference frame, the muons are moving at close to light speed, so their clocks run slow and they survive longer. From the muons' reference frame, time passes normally, but the distance to Earth's surface is contracted. Both perspectives agree on the outcome. This natural experiment has been confirming special relativity continuously since the 1930s. Particle accelerators routinely observe time dilation. In particle accelerators, physicists routinely accelerate particles to velocities approaching the speed of light. At these speeds, time dilation becomes extreme. Unstable particles that would normally decay in microseconds can persist for milliseconds or longer because their internal clocks are running slowly from our perspective. This allows them to travel farther in the laboratory before decaying. The effects are so pronounced that particle physics experiments must account for time dilation in their calculations. It's not exotic theory, but everyday reality in high-energy physics. GPS compensates for time dilation continuously. We've mentioned this before, but it bears emphasizing. GPS satellites experience both special relativistic time dilation due to their motion, which makes their clocks run slow by about 7 microseconds per day, and general relativistic time dilation due to weaker gravity at altitude, which makes their clocks run fast by about 45 microseconds per day. The net effect is clocks gaining about 38 microseconds per day. GPS satellite clocks are deliberately set to run slightly slow before launch so that once in orbit, they'll tick at the correct rate relative to ground clocks. Every location calculation your phone makes relies on these relativistic corrections being accurate. Time moves slower on the first floor than the 10th. General relativity predicts that time runs slightly faster the farther you are from a massive object. This means time flows slightly faster on the 10th floor of a building than on the first floor. The effect is tiny, about 90 nanoseconds per day for a 30-meter height difference, but optical atomic clocks are now sensitive enough to measure it. Physicists have demonstrated this effect by comparing clocks at different elevations, showing that gravity's influence on time is not just a feature of black holes and neutron stars, but operates everywhere, all the time, even over distances we encounter in everyday life. Haffley-Keating experiment confirmed relativity with commercial flights. In 1971, physicists Joseph Haffel and Richard Keating flew cesium atomic clocks around the world on commercial airline flights, some flying eastward, others westward. They predicted, using both special and general relativity, exactly how much time difference should accumulate. Flying eastward, moving faster relative to Earth's center, caused clocks to lose 59 nanoseconds. Flying westward, moving slower relative to Earth's center, caused clocks to gain 273 nanoseconds. The actual measured differences matched predictions to within experimental error, providing elegant confirmation that relativity works not just in thought experiments, but in the real world. Gravitational time dilation affects GPS more than velocity time dilation. For GPS satellites, the gravitational effect is larger than the velocity effect. The satellites are in weaker gravity than Earth's surface, making their clocks run fast by about 45 microseconds per day. Their orbital velocity makes clocks run slow by about 7 microseconds per day. Gravity wins, and the net effect is clocks running fast. This shows that general relativity is not just a small correction to special relativity, but can be the dominant effect even in relatively weak gravitational fields like those around Earth. Time dilation is used in science fiction, sometimes incorrectly. Science fiction often features time dilation, with travelers returning to find centuries have passed. While time dilation is real, achieving significant effects requires extreme velocities or gravitational fields. At 90% light speed, time dilation is noticeable, but not extreme, a factor of about 2. To achieve dramatic effects, like in many science fiction stories, would require velocities above 99%, the speed of light or proximity to black holes. Also, many depictions confuse time dilation with time travel. You can't visit the past through time dilation. You can only slow your journey into the future. Returning to find your twin has aged more doesn't mean you've traveled back in time. It means you've aged less on your journey forward. Every clock experiences its own proper time. In relativity, each clock measures its own proper time, the time experienced along its particular path. Through space-time, there is no universal time that all clocks must agree on. Two clocks following different paths through space-time, especially paths involving different velocities or gravitational potentials, will measure different elapsed times between the same two events. Neither measurement is wrong. They're both correct measurements of proper time along different world lines. This challenges our intuition but is fundamental to how time works in our universe. You are constantly experiencing time dilation. Even now, as you rest and listen to this, you're experiencing time dilation relative to various reference frames. Relative to a satellite orbiting overhead, your time flows slightly slower due to your deeper position in Earth's gravitational field. Relative to particles in a cosmic ray shower, your time flows vastly faster because those particles are moving at near light speed. Time dilation isn't something that only happens in exotic circumstances. It's happening all the time, everywhere, but the effects are usually too small to notice without atomic clocks or particle accelerators. The Planck scale and limits of time. Planck time is the smallest meaningful unit. The Planck time, approximately 5.39 times 10 to the negative 44 seconds, is considered by many physicists to represent the smallest, meaningful unit of time in physics. To write this out in decimal form, you'd write a 0, then a decimal point, then 43 more zeros, then a 5. It's the time it takes light, the fastest thing in the universe, to cross one Planck length, the smallest meaningful distance. Below the Planck scale, quantum fluctuations of space-time itself become so large that our current theories of physics break down completely. The smooth fabric of space-time we experience at human scales dissolves into quantum foam at these tiny distances and durations. You can't meaningfully speak of what happens during an interval shorter than Planck time, because the very concept of time as we understand it, as a parameter marking the sequence of events, ceases to apply. The equations of physics, both quantum mechanics and general relativity, become useless, yielding infinities and paradoxes. It's not just a practical measurement limit, something we might overcome with better technology. The Planck time appears to be a fundamental boundary of physical description, a limit imposed by the structure of reality itself. Below this threshold, space-time may not exist in any way we currently understand. Duration, sequence, causality, all the concepts we use to make sense of time may have no meaning at these scales. The Planck time represents the edge of our knowledge, a boundary where physics meets mystery. A Planck time is unimaginably brief. To appreciate how incredibly short the Planck time is, consider that a Planck time is to 1 second, as 1 second is to about 10 to the 35th power years. The age of the universe is only about 10 to the 10th power years, a mere instant compared to this scale. If you could count Planck times the way you count seconds, there are more Planck times in 1 second than there have been seconds since the Big Bang, times a trillion. This scale is so far removed from human experience that it challenges our ability to comprehend. The Planck epoch was the earliest moment of the universe. The first Planck time after the Big Bang, from 0 to about 10 to the negative 43 seconds, is called the Planck epoch. During this era, the universe was so hot and dense that all 4 fundamental forces, gravity, electromagnetism, strong nuclear, and weak nuclear, may have been unified into a single force. Our current theories cannot describe what the universe was like during the Planck epoch, because we lack a theory of quantum gravity. Whatever happened then remains beyond our theoretical reach, a moment of cosmic time that science cannot yet illuminate. Quantum foam may fill the vacuum. At the Planck scale, quantum uncertainty becomes so large that, according to some theoretical models, space-time itself might fluctuate wildly. John Wheeler proposed calling this hypothetical structure quantum foam, envisioning a seething froth of virtual particles and tiny fluctuations in the geometry of space-time, appearing and disappearing on timescales of Planck time. At scales we experience, space-time seems smooth and continuous. But if we could zoom in to the Planck scale, Wheeler suggested, it might reveal a chaotic, foaming structure. This remains speculative, as we cannot observe it directly, but it emerges naturally from attempts to combine quantum mechanics and general relativity. We have never measured time intervals near Planck time. The shortest time interval ever directly measured is about a zeptosecond, 10 to the negative 21 seconds. This is the time scale on which electrons move within atoms, measured using extremely fast laser pulses. A zeptosecond is to a second, as a second is to about 32 billion years. Yet even this incredibly brief interval is 10 to the 22 times longer than the Planck time. We are nowhere close to measuring time at the Planck scale, and likely never will be with any technology we can currently imagine. The Planck scale suggests a limit to knowledge. Some physicists interpret the Planck scale as a fundamental limit to what can be known, just as Heisenberg's uncertainty principle sets limits on how precisely we can measure position and momentum simultaneously. The Planck scale may set limits on how finely we can probe space and time. This doesn't mean smaller scales don't exist, but it may mean they're forever beyond experimental access, a boundary where physics transitions from empirical science to pure mathematics and philosophy. String theory operates at the Planck scale. String theory, one candidate among several approaches attempting to unify quantum mechanics and gravity, proposes that fundamental particles are not point-like, but tiny vibrating strings. According to this theory, these strings would be incredibly small, with characteristic sizes on the order of the Planck length, vibrating on timescales of the Planck time. Different vibration modes would correspond to different particles. If string theory is correct, the Planck scale would be where the true fundamental description of nature resides. Unfortunately, testing string theory is extraordinarily difficult because the relevant energy scales and time scales are far beyond what we can probe experimentally, and the theory itself remains incomplete and unproven. Loop quantum gravity quantizes space-time. Loop quantum gravity is an alternative approach to quantum gravity that proposes space-time itself is quantized, made up of discrete units at the Planck scale. In this theoretical framework, space is not continuous, but consists of tiny loops and nodes forming what's called a spin network. Time would emerge from the evolution of this network. The minimum loop size would be about 1 Planck length, and these loops would evolve on timescales of Planck time. Loop quantum gravity attempts to describe space-time using quantum mechanics from the ground up, unlike string theory, which adds extra dimensions and structures. Like string theory, however, loop quantum gravity remains a work in progress, with significant mathematical challenges and no experimental verification yet achieved. The Planck's scale unifies fundamental constants. The Planck time is derived from 3 fundamental constants: the gravitational constant, g, Planck's constant h, and the speed of light, c. By combining these in the right way, you get quantities with dimensions of length, time, mass, and so forth. The Planck units are in some sense natural. They're not based on human conventions like the meter or second, but arise from the fundamental structure of physics itself. Any sufficiently advanced civilization in the universe would discover the same Planck units, making them potentially useful for communicating with extraterrestrial intelligence. Time may emerge from timeless physics. Some approaches to quantum gravity suggest that time is not fundamental but emergent, arising from more basic timeless structures. According to these proposals, at the deepest level, the universe might be timeless, described by equations that don't contain time as a variable. Time would emerge only when you look at coarse-grained descriptions or particular subsystems. This is a radical idea that challenges our most basic intuitions. If such theories prove correct, it would mean that the flow of time we experience is not built into the fundamental fabric of reality, but is something that arises secondarily, perhaps from the way conscious observers interact with quantum systems, or from thermodynamic properties of complex systems. However, these ideas remain highly speculative and face significant conceptual and mathematical challenges. The problem of time challenges quantum gravity. In quantum mechanics, time is a parameter. In general relativity, time is part of the dynamical space-time. Combining these views leads to the problem of time. When you write down equations for quantum gravity, time often disappears entirely, leading to the Wheeler-DeWitt equation, which describes a static, unchanging universe. How do you recover the flowing time we experience from this timeless description? This problem has no agreed-upon solution and represents one of the deepest conceptual challenges in theoretical physics. Solving it may require rethinking the nature of time at the most fundamental level. Some theories propose time is discrete, while we experience time as flowing smoothly. Some theoretical approaches to quantum gravity suggest it might actually be discrete at the smallest scales, progressing in tiny jumps of Planck time, rather than continuously. This would make time like a film, a series of individual frames creating the illusion of smooth motion when played at appropriate speed. However, there's currently no experimental evidence for discrete time, and many physicists question this interpretation. Whether time is fundamentally continuous or discrete remains an open question at the boundary of physics and philosophy, one that may require a complete theory of quantum gravity to resolve. Cosmic time in the universe. The universe is 13.8 billion years old. Based on observations of the cosmic microwave background radiation, the expansion rate of the universe, and the abundance of light elements, cosmologists have determined that the universe is approximately 13.8 billion years old. This represents the time since the Big Bang, the moment when space, time, matter, and energy came into existence in an incredibly hot, dense state. This age is remarkably precise, known to within about 1%, a testament to modern observational cosmology. Cosmic time provides a universal reference frame. In an expanding universe, there's a natural notion of cosmic time, the time measured by observers moving with the expansion of the universe, carried along with the cosmic flow. Different observers at rest relative to the cosmic microwave background would all agree on how much time has elapsed since the Big Bang. This provides a kind of universal time standard for cosmology, though it's not absolute time in the Newtonian sense, just a convenient frame of reference based on the universe's large-scale structure. The expansion of space affects time. As the universe expands, the wavelength of light traveling through space stretches, a phenomenon called cosmological redshift. Distant galaxies appear redder because their light has been stretched during its journey to us. This expansion also affects time measurements. A supernova that we observe in a distant galaxy appears to evolve more slowly than a nearby supernova, not because time is actually flowing differently there, but because the light waves are stretched, making everything appear to happen in slow motion. The universe's expansion creates a kind of time dilation effect for very distant objects. The Big Bang was the beginning of time itself. The Big Bang was not an explosion in space, like a bomb going off in an existing void. It was an explosion of space, a violent expansion of the fabric of space-time itself. Space itself came into existence in the Big Bang, emerging from a state of infinite density and temperature, and so did time. There was no space before the Big Bang, because space itself had not yet come into being. There was no time before the Big Bang, because time itself began in that first instant. Asking what happened before the Big Bang may be as meaningless as asking what lies north of the North Pole. The question contains a flaw, because before is a temporal concept, and time didn't exist before time began. This is a profoundly difficult concept to grasp. We're so used to thinking of time as a container in which events happen, an eternal stage upon which the drama of existence plays out. We imagine an empty, timeless void into which the universe suddenly burst into being. But that's not what happened. In cosmology, time is part of what came into existence, emerging from the initial singularity along with space, matter, energy, and the laws of physics themselves. The universe, including time itself, has a finite age of approximately 13.8 billion years, but no edge in time before which it didn't exist. This is one of the deepest and strangest truths about our cosmos. Time is not eternal. It had a beginning. And as strange as it seems, that beginning was not an event that happened at a particular time, but rather the moment when time itself began. Look back time lets us see the universe's history. When we look at distant objects in the universe, we see them as they were in the past, because light travels at finite speed. Light from the sun takes 8 minutes to reach us, so we see the sun as it was 8 minutes ago. Light from the Andromeda galaxy takes about 2.5 million years to reach us, so we see it as it was 2.5 million years ago. The most distant galaxies we observe are seen as they were over 13 billion years ago, when the universe was young. Telescopes are time machines, letting us look back through cosmic history. The cosmic microwave background is light from the early universe. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. At this moment, light could travel freely through space for the first time. This light has been traveling toward us ever since, stretched by cosmic expansion into microwave frequencies. The cosmic microwave background radiation we detect today is a snapshot of the universe at this early time, a fossil light carrying information about conditions in the ancient universe. Black holes distort time on cosmic scales. Supermassive black holes in the centers of galaxies can have masses billions of times that of the sun. The space-time curvature around such objects is extreme. Time near the event horizon of a supermassive black hole flows vastly slower than in intergalactic space. If you could somehow survive close to a black hole's event horizon and eventually escape, you might find that billions of years had passed in the external universe, while only hours passed for you. Black holes create regions where time nearly stops, at least from an outside perspective. Inflation may have occurred in the universe's first instant, according to a widely accepted cosmological model, in the first fraction of a second after the Big Bang. The universe may have undergone a period of exponential expansion called inflation, during a time interval of perhaps 10 to the negative 35 to 10 to the negative 33 seconds. The universe could have expanded by a factor of at least 10 to the 26, possibly much more. Inflation was proposed to solve several cosmological problems and appears to have left imprints in the cosmic microwave background that we can observe today. While inflation has substantial observational support, it remains a theoretical framework rather than established fact, and alternative models continue to be explored. The universe may end in heat death. If the expansion of the universe continues accelerating as current observations suggest, driven by what we call dark energy, the eventual fate appears to be cold and dark. Based on our current understanding, stars will exhaust their fuel and die. Galaxies will fly apart as expansion accelerates. Eventually, perhaps 10 to the 100 years from now, even black holes would evaporate through Hawking radiation, a process that itself remains theoretical. The universe would reach maximum entropy, a state of uniform temperature near absolute zero with no available energy to do work. This heat death represents the end of time, Not because time stops existing, but because nothing happens anymore. Without change, time loses meaning. However, our understanding of dark energy remains limited, and the universe's ultimate fate is still an open question. Time may be cyclic in some models. Some cosmological models propose that the universe undergoes endless cycles of expansion and contraction, big bangs followed by big crunches, followed by new big bangs. In such scenarios, time might extend infinitely into the past and future, with each cycle potentially having different physical laws. Our Big Bang might not be the beginning of time, but just one in an infinite series. These cyclic models remain speculative alternatives, and current observations favor continued expansion rather than eventual contraction. But they represent possibilities for time on the grandest scale that some researchers continue to explore. We are made of material cooked in stars billions of years ago. The atoms in your body, except for hydrogen, were forged in the nuclear furnaces of stars that lived and died billions of years ago. Carbon, oxygen, nitrogen, calcium, iron, all the elements essential for life were created through nuclear fusion in stars and scattered through space when those stars exploded as supernovae. You are literally made of stardust. Your atoms have existed since shortly after the Big Bang, cycling through generations of stars over billions of years. In a very real sense, you contain within you the entire history of the universe's evolution. Philosophical and psychological time. Time perception varies with age. Ask a child how long an hour feels, and you'll get a very different answer than from an elderly person. This isn't just subjective. There are neurological reasons why time seems to speed up as we age. When you're young, every experience is new. Your brain is constantly forming new memories, and this gives the subjective sense that more time is passing. As you age, routine sets in. Fewer novel experiences mean fewer distinct memories, and time seems to pass more quickly. A year to a 5-year-old is 20% of their entire life, but to a 50-year-old it's only 2%, which may also contribute to the perception. The species present is the window of now. When you experience the present moment, what you're actually experiencing is not a single instant, not a mathematical point with zero duration, but a window of time, typically lasting anywhere from a few hundred milliseconds to a few seconds. This is called the specious present, a term coined by philosopher William James, and it represents the span over which your brain integrates sensory information to create the subjective experience of now. Events within this window feel simultaneous, even though they occur at slightly different times. When you watch someone speak, you perceive their lip movements, and the sound of their voice is happening together, in perfect synchrony, even though the visual information reaches your brain slightly before the auditory information. Your brain performs remarkable temporal integration, aligning these signals to create a coherent experience of the present moment. This integration is necessary for making sense of the world. If you only experience true mathematical instants with no duration, you couldn't perceive motion, which requires comparing an object's position across time. You couldn't understand speech, which depends on processing sequences of sounds. You couldn't experience music, where notes must be held in memory and related to each other to create melody and rhythm. The flowing present you experience, the sensation that now has some thickness and duration, is constructed by your brain from the raw data of sensory experience. Neuroscientists have discovered that different types of perception have different integration windows. Visual information is integrated over about 1/10 of a second, auditory information over slightly longer periods, the sense of touch over even briefer intervals. Your brain constantly performs this temporal binding, creating a unified experience of the present, from sensory information arriving at different times through different channels. The now you experience is not the now that physics describes. It's a psychological construct, a perceptual window that allows consciousness to function in a world of continuous change. Time flies when you're having fun. Strong emotions and engaging activities make time seem to pass quickly in the moment, while boring or fearful situations make time drag. But in memory, the pattern reverses. Periods filled with novel, emotional experiences create many detailed memories and seem longer in retrospect. Boring periods create few memories and seem shorter when remembered. This creates interesting effects. A vacation packed with new experiences might fly by while you're living it, but seem long when you look back. Routine work weeks drag while you're in them, but blur together in memory. Flow states alter time perception. When deeply engaged in an activity, athletes, artists, and others sometimes experience flow states where they're completely absorbed. During flow, time perception can radically shift. Hours can feel like minutes. This isn't just distraction. It represents a different mode of consciousness, where self-awareness fades and action becomes automatic. The exact mechanisms are still being studied, but flow states appear to involve changes in brain activity, particularly in regions associated with self-monitoring and time perception. Does the present even exist? Philosophers have long debated whether the present has any special reality. Augustine famously wrote that the past no longer exists, the future does not yet exist, and the present has no duration. If the present is infinitesimally thin, does it exist at all? Or is what we call the present just the boundary between past and future, a mathematical abstraction rather than something real? Some interpretations of physics, particularly the block universe view, suggest that all moments are equally real, and the flowing present is an illusion of consciousness. The arrow of time may be linked to consciousness. Some philosophers and physicists have suggested that consciousness itself might be intimately connected to the arrow of time. The formation of memories, the experience of causation, the sense of free will, all depend on time having a direction. A few researchers have even proposed the more controversial idea that consciousness somehow selects or creates the direction of time, though this remains a minority view. These ideas remain highly speculative and contentious, straddling the boundary between physics, neuroscience, and philosophy. But they point to deep, unanswered questions about the relationship between subjective experience and objective physical time. Time is relative to culture and language. Different cultures conceptualize and talk about time differently. Some languages don't have future tense. Others have elaborate systems of tenses that English lacks. Some cultures think of time as cyclical, others as linear. The Western industrial notion of time as a resource to be managed and spent is not universal. These differences aren't just linguistic, but reflect different ways of experiencing and organizing time. While physics gives us objective measurements, the meaning and experience of time are shaped by culture, language, and individual psychology. Can we time travel? This is perhaps the most romantic question about time. Physics allows for time travel to the future through time dilation. You just need to move very fast or spend time near a black hole, and you'll find when you return that more time has passed elsewhere. You've effectively traveled into the future. But traveling to the past appears far more problematic, leading to paradoxes like the grandfather paradox. If you went back and prevented your own birth, how could you exist to go back in the first place? Some physicists have explored potential solutions involving parallel timelines or self-consistent causal loops, but most believe the laws of physics probably prohibit backward time travel. The question isn't entirely settled, as we don't yet have a complete theory of quantum gravity, but the consensus view is that the past remains inaccessible. Déjà vu and temporal illusions. Sometimes we experience the eerie sensation that we've lived a moment before, déjà vu, or we might experience jamais vu, where familiar things suddenly seem strange and unfamiliar. These temporal illusions reveal how constructed our sense of time is. Memory errors, timing mismatches in neural processing, or unusual states of brain activity can create these experiences. They remind us that our experience of time is a mental construction, not a direct perception of external reality. The brain builds our temporal experience from fragments, and sometimes the building process creates glitches. Time as the ultimate mystery. After all we've explored tonight, from quantum mechanics to cosmology, from ancient sundials to atomic clocks, time remains mysterious. We can measure it with extraordinary precision. We understand how it dilates and how it relates to entropy. We've traced its arrow from the Big Bang to potential heat death. Yet the fundamental nature of time, whether it's truly fundamental or emergent, whether it flows or is merely a dimension we move through, why it has a direction, how it relates to consciousness, these questions remain open. Time is woven into every aspect of existence, and yet its deepest nature eludes us. Perhaps that's fitting. Perhaps time, like existence itself, is not something to be fully solved, but something to be experienced, wondered about, and investigated endlessly. Conclusion. And now our journey through 100 facts about time comes to rest, like a pendulum gradually slowing, like photons from distant stars finally reaching their destination after crossing the vast dark between galaxies. We've wandered from the infinite to the infinitesimal, from Planck time to cosmic time, from the strictest precision of atomic clocks, measuring nanoseconds, to the subjective flow of conscious experience, where minutes can feel like hours, or hours like minutes. You've heard how time bends near massive objects, warping like rubber, stretched by a heavy weight, how it slows for moving clocks, creating the twin paradox where identical siblings age at different rates, how it began with the universe itself in the Big Bang, emerging from nothing along with space, matter, and energy, and may end in heat death trillions of years hence, when the last star has burned out and the last black hole has evaporated into the cold dark. You've learned that time might not be fundamental, that at the deepest levels of quantum reality, it may emerge from something even more basic, that the present, this moment you're experiencing right now, has no duration, exists for literally 0 seconds, a mathematical point, infinitely thin, sliding along the timeline. That memory and entropy give time its arrow, its direction, its flow from past through present into future. You are a creature of time, sculpted by it, defined by it, utterly dependent upon it. Every atom in your body has traveled through billions of years of cosmic history. The iron in your blood was forged in the heart of a star that exploded before our sun even existed. The calcium in your bones, the carbon in your cells, the oxygen in your lungs, all cooked in stellar furnaces and scattered through space by supernova explosions billions of years ago. You exist in this moment, this impossibly thin boundary between past and future, carried forward by the universe's expansion and the inexorable increase of entropy. Time flows through you with every heartbeat, roughly 60 to 80 beats per minute, adding up to over 2 billion beats in an average lifetime. With every breath, 16 to 20 breaths per minute, each one moving air through your lungs in a rhythm as old as land-dwelling life. Every neural firing that creates the stream of consciousness you experience as now, electrical signals cascading through billions of neurons, creating the seamless flow of subjective time, The feeling that you're experiencing a continuous present moment when really you're experiencing discrete moments integrated together by your brain's extraordinary processing. Tonight, as you drift into sleep, time continues its patient work, neither accelerating nor slowing, flowing at its steady rate in your reference frame. Your brain will consolidate memories, moving experiences from short-term to long-term storage, deciding which moments from today are worth keeping and which can be discarded. Your body will repair itself, cells dividing, proteins being synthesized, damage being fixed at the molecular level. The Earth will turn at 1,000 miles per hour at the equator, completing another rotation in its endless spin. The planet will move nearly 2 million miles along its orbit around the Sun, and the universe will expand, stretching the fabric of space, causing distant galaxies to recede from us ever faster, driven by the mysterious dark energy that fills the cosmos. When you wake, you'll have traveled several hours into the future, aged imperceptibly, perhaps 30,000 heartbeats older, existed through one more rotation of this ancient planet in its orbit around an ordinary star in an ordinary galaxy in a universe containing hundreds of billions of such galaxies. The photons that left the Sun 8 minutes before you wake will just be arriving, having traveled 93 million miles through the vacuum of space to warm your morning. And if these calm, curious explorations have helped you unwind, if they've given you something to ponder as you drift off into sleep, if they've sparked wonder or curiosity, or simply provided a pleasant background for relaxation, consider liking this video and subscribing to Whispered Knowledge. It helps others find their way here too, one sleepy soul at a time, each discovering that the universe is stranger and more wonderful than we imagined, that time is both the most familiar and most mysterious aspect of existence. Sleep well, dream softly, and remember, time is always passing, flowing like an invisible river carrying us all forward. But for now, right now in this moment, you have nowhere to be except right here, drifting gently through the only moment that ever truly exists, the eternal now. Rest in the knowledge that you're part of something vast and ancient, a universe 13.8 billion years in the making, and that your atoms will continue their journey long after your consciousness has faded, cycling through stars and planets and perhaps other living things, timeless travelers in a cosmos where time itself may be an illusion. Good night.